Once you begin to grasp the scale of the Oort cloud, a new question naturally follows. If this distant sphere is so vast, how many objects could it possibly contain? It is a simple question in wording, but a difficult one in practice. Unlike counting planets or even Kuiper belt objects, we cannot scan the Oort cloud with telescopes and tally what we see. The cloud is too distant, too faint, and its members are too small and dark to observe directly. So instead of counting objects, astronomers estimate them. That distinction matters. When you hear that the Oort cloud may contain trillions of icy bodies, that number is not the result of direct observation. It is the result of modelling, statistics, and inference drawn from the behaviour of comets that briefly visit the inner solar system. To understand how these estimates are made, we need to return to the long-period comets that first inspired Jan Oort's proposal. Each time a long-period comet appears, astronomers calculate its orbit carefully. They determine how elongated it is, how long it takes to complete a full revolution around the Sun, and how strongly it is bound gravitationally. By tracing the comet's path backward, they can estimate how far from the Sun it likely originated. When enough of these comets are studied, patterns emerge. Astronomers can estimate how frequently new long-period comets enter the inner solar system. They can measure how many appear per year, per decade, per century. From that rate, they work backward. If, for example, a certain number of comets are observed entering the inner solar system each year, and if models of gravitational perturbations suggest that only a tiny fraction of Oort cloud objects are nudged inward over a given timescale, then the total population must be large enough to sustain that influx over billions of years. This reasoning leads to estimates that the Oort cloud could contain on the order of hundreds of billions to trillions of icy bodies larger than a few kilometres across. But these numbers come with uncertainty. First, we do not detect every long-period comet. Many are faint. Some approach the Sun on trajectories that make them difficult to observe from Earth. Others disintegrate before becoming bright enough to notice. Our observational record is incomplete. Second, the rate at which comets are nudged inward depends on complex gravitational influences. Passing stars, galactic tides, and planetary perturbations all play a role. Small changes in these assumptions can lead to large changes in estimated population size. Even with these uncertainties, however, most models agree that the Oort cloud likely contains far more objects than the Kuiper belt. The Kuiper belt may hold millions of objects larger than 1 kilometre. The Oort cloud, by contrast, may hold trillions. That difference is not just incremental, it reflects the sheer volume of space the cloud occupies. Earlier we discussed how the volume of a sphere increases with the cube of its radius. If the Oort cloud extends 1,000 times farther than the Kuiper belt, its volume could be roughly 1 billion times greater. Now, this does not mean it contains 1 billion times more mass. The density of objects decreases dramatically with distance. The cloud is sparse, extremely sparse. If you were floating somewhere within the Oort cloud, the nearest object might be tens of millions of kilometres away. That is farther than the distance between Earth and the Moon, perhaps comparable to the distance between planets in the inner solar system. This sparsity is why the cloud remains invisible. Another factor to consider is size distribution. Not all Oort cloud objects are the same size. Some are likely small fragments, perhaps only a few hundred metres across. Others may be several kilometres in diameter. A small fraction could be tens or even hundreds of kilometres wide. The larger the object, the fewer there are likely to be. This follows a general rule observed throughout the solar system. Small bodies are far more numerous than large ones. So when astronomers say trillions of objects, they are typically referring to bodies above a certain minimum size, often around 1 kilometre in diameter. Below that size, the number of objects could be much higher, but they would contribute little to the overall mass. Speaking of mass, estimates of the total mass of the Oort cloud vary. Early calculations suggested it might contain several Earth masses of material. More recent models tend to favour lower values, perhaps around 1 to a few Earth masses in total. That might sound like a lot, but remember how vast the volume is. Spread across a sphere tens of thousands of astronomical units in radius, even several Earth masses amount to a very low average density. For comparison, the mass of Jupiter alone is more than 300 times the mass of Earth. All of the Oort cloud combined likely contains less mass than a single giant planet. This tells us something important. The Oort cloud is large in extent, but not in mass concentration. It is a dispersed archive of leftover building blocks, not a hidden giant planet. Another interesting question is how many of these objects have ever visited the inner solar system. Each long-period comet that approaches the Sun represents one of these distant bodies temporarily drawn inward. Some may pass once and then be ejected from the solar system entirely. Others may be captured into shorter period orbits, gradually losing mass over repeated passes. Over billions of years, countless Oort Cloud objects have likely made this journey inward. This process gradually depletes the cloud. So how has it survived for 4.5 billion years? The answer likely lies in its size. If the initial population was extremely large, then even a steady trickle of inward comets would not exhaust it quickly. Additionally, the inner Oort cloud may act as a reservoir, feeding the outer regions and replenishing objects lost to interstellar space. There is also the possibility of capture. Occasionally, interstellar objects pass near the Sun. We have direct evidence of this in the form of objects like Oumuamua and Comet Borisov, which entered the solar system from interstellar space. If such objects pass close enough and at the right speed, it is theoretically possible for them to become gravitationally bound to the Sun, joining the distant cloud. This would mean the Oort cloud is not purely a collection of native solar system material. It could include interstellar immigrants as well. Another layer of uncertainty comes from the cloud structure. Astronomers often distinguish between the inner Oort cloud and the outer Oort cloud. The inner region may be more densely populated and more tightly bound to the Sun. The outer region may be sparser and more vulnerable to disruption. If the inner cloud contains most of the mass, then the outer cloud may act primarily as a source of long-period comets. Some models even suggest that the inner Oort cloud could contain 10 times as many objects as the outer cloud, though these numbers are highly uncertain. All of these estimates depend on assumptions about the early solar system. How many planetesimals were scattered outward by Jupiter and Saturn? How densely packed was the Sun's birth cluster? How frequently did other stars pass nearby in the early days? How strong are galactic tidal forces over billions of years? Each of these variables influences the final population. Because we cannot observe the cloud directly, we rely on computer simulations to test different scenarios. These simulations track millions of virtual objects over billions of simulated years, modelling gravitational interactions and perturbations. When the output of these simulations matches the observed distribution of long-period comets, astronomers gain confidence that the assumed population size is plausible. It is a kind of reverse engineering. We observe the comets that arrive, we infer the size of the distant reservoir needed to supply them, and yet, even with all of this modelling, there remains a wide margin of uncertainty. The Oort cloud could contain hundreds of billions of objects. It could contain trillions. The true number might lie somewhere in between. What is clear is that the cloud represents a vast population of icy remnants, far exceeding the number of large bodies in the planetary region, and this has implications beyond simple counting. Each of those objects is a frozen relic of the early solar system. Preserved at extreme distances and low temperatures, they may contain pristine material from the time when the Sun and planets were forming. Long-period comets that reach the inner solar system offer rare opportunities to study this material. They are samples delivered from the outermost archive. So when we ask how many objects are out there, we are not merely asking for a statistic. We are asking how extensive this ancient archive might be. A sphere stretching nearly halfway to the nearest star, containing perhaps trillions of icy fragments, each one orbiting in silence for millions of years. That is the scale of the population we are considering. Long before the outer reaches of the Oort cloud begin to fade into the gravitational background of the galaxy, there is another region that demands attention. It is closer, denser, and far more tightly bound to the Sun, yet it remains just as unseen. This is what astronomers refer to as the inner Oort cloud, sometimes called the Hills cloud, a hidden shell of icy bodies occupying the deep outer reaches of the Sun's gravitational domain. It is called hidden not because it is mysterious in a dramatic sense, but because it sits at a distance where direct observation becomes almost completely impractical. Even compared to the Kuiper belt and scattered disk, the inner Oort cloud lies far beyond the reach of routine telescopic surveys, and yet paradoxically, it may contain a substantial fraction of the Oort cloud's total population. To understand why astronomers believe such a region exists, it helps to return to the problem that first motivated the idea of the Oort cloud itself. Long-period comets arrive from all directions, but their behaviour is not uniform. Some appear to originate from extremely distant orbits, barely bound to the Sun. Others seem to come from orbits that are distant but not quite so fragile. When researchers began running detailed simulations of comet dynamics, they noticed something interesting. A single, uniform cloud extending from a few thousand astronomical units all the way to the Sun's gravitational limit did not always reproduce the observed comet behaviour very well. The numbers worked better when the cloud was layered. In these models, an inner reservoir of objects sits closer to the Sun, more securely bound, and more resistant to disruption. This inner population acts as a long-term storage zone, slowly feeding objects into the outer cloud and occasionally into the inner solar system. The inner Oort cloud is thought to begin somewhere around 2,000 astronomical units from the Sun. Some estimates place its outer boundary at around 20,000 astronomical units. Others extend it farther. The exact numbers vary, but the key idea remains the same. This is a region far beyond the Kuiper belt and scattered disk, yet significantly closer than the most distant reaches of the outer Oort cloud. At 2,000 astronomical units, sunlight from the Sun takes about 11 days to arrive. At 10,000 astronomical units, that travel time stretches to nearly 2 months. At 20,000 astronomical units, it takes more than 3 months. These are distances where the Sun is no longer a dominating presence in any visual or thermal sense, but where its gravity still holds firmly. This firmness is what distinguishes the inner Oort cloud from the outer one. Objects in the inner cloud are more tightly bound to the Sun. Their orbits, while elongated and tilted, are less susceptible to being stripped away by passing stars or by the slow pull of the Milky Way's gravitational field. They are still vulnerable, but not precariously so. This stability makes the inner Oort cloud especially important when considering the long-term survival of the entire structure. Over billions of years, the outer Oort cloud is expected to lose a significant number of objects. Some are ejected by stellar encounters, others drift away under galactic tides. Without a replenishing source, the outer cloud would gradually thin out. The inner Oort cloud may be that source. In many models, objects from the inner cloud are slowly transferred outward through gravitational interactions. Once they reach the outer cloud, they become more vulnerable and can eventually be perturbed inward as long-period comets. In this view, the inner Oort cloud is not merely a passive region. It is an active reservoir, maintaining the supply of distant icy bodies over cosmic timescales. This idea also helps address another puzzle. If the Oort cloud formed early in the solar system's history, when the Sun was still embedded in a dense stellar cluster, then close stellar encounters would have been more common. Such encounters could have stripped away loosely bound objects, especially from the outer regions. A more tightly bound inner cloud would have been more resistant to this early erosion, even as the Sun migrated out of its birth cluster and into a quieter region of the galaxy. The inner cloud could have survived largely intact. That survival would explain why the Oort cloud still exists today, billions of years later. The shape of the inner Oort cloud is also likely different from that of the outer cloud. While the outer cloud appears roughly spherical, the inner cloud may be more flattened or elongated. Some simulations suggest it could retain a memory of the original plane of the solar system, at least to a degree. Over time, perturbations would still randomize orbits, but not as completely as in the outer regions. This means the inner Oort cloud may not be a perfect shell. It may be more like a thick, distorted halo, transitioning gradually into the fully spherical outer cloud. Because of its location, the inner Oort cloud is also the most plausible source of objects like Sedna. Sedna's orbit is unusual. Its closest approach to the Sun is far beyond Neptune, and its farthest distance reaches nearly 1,000 astronomical units. It does not appear to be strongly influenced by the known planets. Its orbit suggests it was shaped by forces acting at much greater distances. Sedna may be a member of the inner Oort cloud, or at least a transitional object between the scattered disk and the inner cloud. Other similar objects have been discovered, though they are rare and difficult to detect. These discoveries lend weight to the idea that the inner Oort cloud exists, and that it begins closer to the Sun than the outer cloud. Another reason astronomers take the inner Oort cloud seriously is related to efficiency. If the Oort cloud consisted only of an extremely distant outer shell, it would be difficult to maintain the observed rate of long-period comets over billions of years. Too many objects would be lost too quickly. The numbers would not add up unless the initial population were implausibly large. By introducing a denser inner reservoir, models become more realistic. The inner cloud can act as a buffer, slowly resupplying the outer cloud and maintaining the comet flux we observe today. This layered structure also affects how comets enter the inner solar system. An object in the inner Oort cloud is less likely to be directly perturbed into a sun-grazing orbit. Instead, it may first be nudged outward into the outer cloud, where it becomes more vulnerable to further perturbations. Only then does it have a significant chance of being sent inward as a long-period comet. This two-step process helps explain why long-period comets are relatively rare despite the enormous size of the Oort cloud. The inner Oort cloud may also play a role in shaping the distribution of cometary energies. Some long-period comets appear to be more tightly bound to the Sun than others. This suggests they originated from a region where gravitational binding was stronger, consistent with an inner cloud source. Others arrive on orbits that are barely bound, suggesting an origin in the outer cloud. Taken together, these observations point toward a multi-layered structure rather than a single homogeneous shell. Now consider density again, but with more nuance. The inner Oort cloud is still extremely sparse by everyday standards. Objects are separated by vast distances, but compared to the outer cloud, it may be relatively crowded. Crowded here does not mean close, it means less distant. If the outer cloud contains trillions of objects spread across an enormous volume, the inner cloud may contain a comparable number concentrated into a much smaller volume. This would increase its average density significantly, even if that density remains extraordinarily low. This distinction matters because density influences how often objects interact gravitationally, how stable their orbits are, and how likely they are to be perturbed inward or outward. The inner Oort cloud's greater density and stronger binding make it more resilient. It is harder to disrupt. It evolves more slowly. This slow evolution is part of what makes it so difficult to study. Changes in the inner cloud occur over millions or billions of years. Human observation spans only a tiny fraction of that time. We see snapshots, not motion. We infer structure from statistical patterns rather than direct evidence. Even with modern telescopes, we're unlikely to ever image the inner Oort cloud directly. Its objects are too faint. Their reflected sunlight is negligible. They emit no detectable radiation of their own. Future surveys may detect more Sedna-like objects, giving us better constraints on the inner cloud's size and shape. But a detailed map remains out of reach. In this sense, the inner Oort cloud is one of the largest unseen structures associated with the Sun. It is a hidden shell not because it is imaginary, but because it operates on scales that push beyond observational capability. Another intriguing aspect of the inner Oort cloud is its potential role as a record of the Sun's early environment. The orbits of its objects may preserve information about how close other stars passed during the solar system's youth. Different encounter histories produce different orbital distributions. By studying the orbits of distant objects, astronomers may eventually be able to reconstruct aspects of the Sun's birth cluster. In that way, the inner Oort cloud is not just a reservoir of icy debris, it is an archive of dynamical history. Each object carries information about past gravitational interactions. Taken together, they form a fossil record written not in rocks or ice cores, but in orbital parameters. As we move outward in our exploration, the inner Oort cloud serves as a bridge. It connects the relatively familiar territory of the Kuiper Belt and scattered disk with the extreme, barely bound realm of the outer Oort cloud. It explains how such a vast structure can persist. It clarifies why the comet population behaves the way it does, and yet, for all its importance, it remains invisible. We know it exists not because we see it, but because without it, the solar system's behaviour would be harder to explain. This hidden shell reminds us that size alone does not determine significance. Sometimes the most important regions are those that quietly maintain balance over immense spans of time. Once you move beyond the inner reservoir, the nature of the solar system changes again. The transition is not abrupt, and there is no clear marker you can point to and say, here is where everything shifts. Instead, the structure simply grows thinner, looser, and more vulnerable. This is the outer Oort cloud, the region that most people have in mind when they hear the phrase at all. It is also the place where the idea of the solar system having an edge becomes difficult to defend. The outer Oort cloud is often described as the solar system's fuzzy boundary, and that description is more literal than it might sound. Fuzzy does not mean unclear because of ignorance. It means unclear because the physics itself does not produce a sharp line. The farther you go from the Sun, the weaker its gravitational grip becomes, and the more other influences begin to matter. This outer region is thought to begin somewhere beyond the inner cloud, perhaps around 20,000 astronomical units from the Sun. Some models place the transition closer, others place it farther out. The uncertainty exists because the boundary is defined by behaviour rather than location. Objects in this region are still bound to the Sun, but only loosely. Their orbits are extremely elongated. Their binding energy is low. Small disturbances can have large effects. At distances of 20,000 astronomical units, sunlight from the Sun takes nearly 3 months to arrive. At 50,000 astronomical units, it takes over 8 months. At 100,000 astronomical units, light travels for more than a year and a half before reaching these distant bodies. By any intuitive standard, this is no longer the solar system we're used to thinking about, and yet gravity still reaches that far. The defining feature of the outer Oort cloud is not its size alone, but the delicacy of its balance. Objects here exist in a gravitational tug-of-war. On one side is the Sun, whose pull weakens steadily with distance. On the other side are the combined influences of the Milky Way and passing stars. The Milky Way's gravitational field exerts what astronomers call a galactic tide. This is not a sudden force, but a slow, persistent stretching effect caused by the uneven distribution of mass in the galaxy. Near the Sun, this tidal force is negligible compared to solar gravity. But at tens of thousands of astronomical units, the balance begins to shift. For an object in the outer Oort cloud, the Sun is no longer the only significant gravitational influence. The galaxy itself starts to matter. This is why the outer Oort cloud is so effective at producing long-period comets. Galactic tides can gently alter the orbits of distant objects over millions of years. These changes are subtle, but they accumulate. Eventually an object's orbit may be reshaped just enough that its closest approach to the Sun moves inward. Once that happens, the object begins a long fall toward the inner solar system. Passing stars add another layer of complexity. The Sun does not remain stationary. It orbits the centre of the Milky Way, and along that path it occasionally passes relatively close to other stars. Close, in this context, may mean within a light year or two. Even at those distances, a star's gravity can perturb the outer Oort cloud. Each stellar encounter slightly rearranges the cloud. Some objects are nudged inward, others are pushed outward. A few may be stripped away entirely and lost to interstellar space. Over billions of years, these encounters reshape the cloud again and again. This constant reshaping is why the outer Oort cloud cannot be thought of as a static shell. It is dynamic, but dynamic on timescales far longer than human history. Changes occur slowly, invisibly, accumulating over epochs. Because of this, the outer boundary of the Oort cloud is not fixed. It expands and contracts depending on the Sun's environment. Early in the solar system's history, when the Sun was likely part of a dense stellar cluster, close encounters would have been more frequent. During that time, the outer cloud may have been more heavily eroded. Many loosely bound objects could have been stripped away before the Sun ever left its birth cluster. As the Sun migrated into a quieter region of the galaxy, the rate of disruptive encounters decreased. The outer Oort cloud became more stable, though still vulnerable. This history means that the present-day size of the outer Oort cloud reflects not just the Sun's formation, but its entire journey through the Milky Way. Another important characteristic of the outer cloud is its extreme sparsity. Even if it contains trillions of objects, those objects are spread across an enormous volume. The average distance between neighbouring bodies may be measured in millions or tens of millions of kilometres. Collisions are extraordinarily rare. Interactions between objects are minimal. Each follows its own lonely path. This sparsity has consequences. Because objects rarely interact with one another, the structure of the outer Oort cloud is dominated by external forces rather than internal dynamics. Galactic tides and stellar encounters matter far more than mutual gravitational interactions between cloud members. In that sense, the outer Oort cloud is less like a swarm and more like a population of independent travellers who happen to share a common gravitational anchor. This independence also contributes to the randomness of comet arrival directions. When an object from the outer cloud is perturbed inward, the direction it approaches the Sun depends on the specifics of the perturbation. There is no preferred plane. There is no dominant orientation. The result is a nearly isotropic distribution of long-period comets, This isotropy is one of the strongest pieces of evidence supporting the outer Oort cloud's spherical nature. Now consider what happens to objects at the very edge. At distances approaching 100,000 astronomical units, the Sun's gravitational pull is extremely weak. Objects here are barely bound. Their orbits are so fragile that even modest disturbances can unbind them completely. At this boundary, the distinction between solar system object and interstellar object becomes ambiguous. An object drifting in this region may be bound to the Sun for millions of years, then lost during a stellar encounter, then perhaps captured by another star, or simply wander through the galaxy indefinitely. This is why the outer Oort cloud is often described as a transitional zone rather than a boundary. It is the region where the solar system fades into the galaxy rather than ending abruptly. If you were to draw a map of the Sun's gravitational influence, the outer Oort cloud would appear not as a circle with a sharp edge, but as a gradually fading density gradient. The probability of finding sunbound objects decreases with distance, rather than dropping to zero at a specific radius. This probabilistic nature makes the question, where does the Oort cloud end, difficult to answer definitively. Some astronomers define the outer edge as the distance at which the Sun's gravity becomes weaker than the average galactic tide. Others define it as the distance beyond which objects are unlikely to remain bound for more than a few million years. Still others use observational constraints derived from comet energies. Each definition yields a slightly different number. This is why you will see estimates ranging from 50,000 to 100,000 astronomical units, and occasionally even beyond. None of these numbers are wrong. They are describing different aspects of the same fuzzy boundary. Another subtle feature of the outer Oort cloud is its interaction with interstellar space. Because this region overlaps with the broader galactic environment, it may serve as a gateway for material exchange between star systems. Objects stripped from one star's cloud may wander through the galaxy and eventually pass near another star. Some may be captured. This means that the outer Oort cloud may contain objects that did not originate with the Sun at all. The discovery of interstellar objects like Oumuamua and Comet Borisov confirms that such wanderers exist. While those particular objects pass through the inner solar system, many more likely pass through the outskirts unnoticed. If capture is possible, even rarely, then over billions of years the outer Oort cloud could accumulate a mixed population. Some objects would be native solar system debris, others would be immigrants. This possibility adds another layer of fuzziness to the boundary. Ownership becomes a matter of timescale rather than origin. An object might be bound to the Sun today, unbound tomorrow, and bound again to another star millions of years later. In this context, the outer Oort cloud is not just a reservoir of icy debris, it is a dynamic interface between stars. Now think again about scale. If the outer Oort cloud extends 1.6 light-years from the Sun, and the nearest star lies 4.37 light-years away, then the gap between stars is not empty of influence. The gravitational domains of stars overlap in subtle ways. They brush against each other. This challenges the intuitive picture of stars as isolated islands separated by vast, empty oceans. In reality, their outermost gravitational reaches interpenetrate, creating a complex web of influence across the galaxy. The outer Oort cloud is where this interpenetration begins. This realization has implications for how we define the solar system itself. If we define it by planets, the solar system is compact. If we define it by heliospheric influence, it is larger. If we define it by gravitational binding, it becomes enormous, extending nearly halfway to the nearest star. Each definition is valid within its context, but none captures the whole picture. The outer Oort cloud reminds us that natural systems do not always conform to human categories. They blend, they overlap, they fade rather than end. This fuzziness is not a flaw. It is a feature of systems governed by gravity across immense distances and timescales. Another important consequence of this fuzziness is uncertainty and long-term stability. Objects in the outer Oort cloud are not guaranteed to remain bound forever. Over billions of years, a significant fraction will be lost. The cloud slowly erodes. Estimates suggest that the present-day Oort cloud may contain only a fraction of the objects it once did. The rest have been ejected into interstellar space. This erosion continues today, albeit slowly. At the same time, new objects may be captured. The cloud evolves. In that sense, The outer Oort cloud is not a relic frozen in time. It is an active participant in galactic dynamics. From the perspective of the inner solar system, this activity is almost imperceptible. Long-period comets arrive only occasionally. Most people will never see one in their lifetime. But on cosmic timescales, these arrivals are part of a steady flow. Each long-period comet that appears is evidence of the outer Oort cloud's ongoing interaction with the galaxy. It is a reminder that the solar system is not a closed box. As we move forward, the existence of this fuzzy boundary forces us to confront another question. If the Sun's grip weakens gradually, and the galaxy's influence grows stronger with distance, where exactly does the Sun lose control? Is there a point beyond which objects are no longer meaningfully part of the solar system at all? And how do astronomers define that transition in practical terms? Far from the warmth and brightness that define the inner solar system, there comes a region where gravity itself begins to hesitate. Not because it vanishes, and not because it suddenly fails, but because it is no longer alone. This is the realm where the Sun's influence thins, to the point that other forces begin to compete, on nearly equal footing. Understanding this region is essential, because it is here that the idea of ownership, of belonging to a star, becomes uncertain. Gravity is often described as infinite in reach, and in a strict mathematical sense that is true. The Sun's gravity extends outward without an abrupt cut-off. Its pull weakens with distance, following a simple inverse square law, but it never fully disappears. If that were the only consideration, the solar system would have no edge at all. Every particle in the universe would be influenced, however faintly, by every other particle. In reality, though, gravity operates in a crowded universe. The Sun is not alone in space. It is embedded within the Milky Way, surrounded by stars, gas, dust, and dark matter. Each of these contributes to a complex gravitational environment. At close distances, the Sun dominates completely. At great distances, it does not. So when we ask where the Sun loses its grip, we are not asking where gravity ends. We are asking where the Sun stops being the most important gravitational influence acting on an object. Near Earth, the answer is obvious. The Sun's gravity governs planetary motion with overwhelming authority. The gravitational pull of Jupiter, the Moon, or even the galaxy itself is negligible by comparison. As you move outward past the planets, that dominance weakens, but it remains unquestioned through the Kuiper belt and into the scattered disk. Even within the inner Oort cloud, the Sun still clearly rules. Objects there are weakly bound, but bound nonetheless. Their orbits are long and tilted, but they are not easily stripped away. A passing star would need to come relatively close to have a dramatic effect. The outer Oort cloud is different. At distances of tens of thousands of astronomical units, the Sun's gravitational pull has diminished to a whisper. It still shapes motion, but it is no longer overwhelming. Other influences become relevant, not as sudden disruptions, but as persistent, cumulative forces. One of the most important of these is the gravitational field of the Milky Way itself. The galaxy is not a point mass, it is a vast distribution of matter, including stars, gas, and a large halo of dark matter. The Sun orbits the galactic centre at a distance of about 26,000 light-years, moving at roughly 220 kilometers per second. As it does so, it experiences tidal forces caused by the uneven distribution of mass within the galaxy. These galactic tides are extremely weak compared to the Sun's gravity near the planets. But at the outer edge of the Oort cloud, they become significant. A tidal force works by stretching and compressing objects due to differences in gravitational pull across space. In the case of the Oort cloud, the galaxy's tidal field can slowly distort the orbits of distant objects, changing their shapes and orientations over millions of years. For an object deep in the outer cloud, this galactic influence can be comparable to the Sun's pull. This balance point is one way to define where the Sun loses its grip. Another important factor is stellar encounters. As the Sun moves through the Milky Way, it occasionally passes near other stars. These encounters are not frequent on human timescales, but over billions of years they are inevitable. A star passing within a light year or two can exert a measurable gravitational influence on the outer Oort cloud. Such encounters do not need to be close to have an effect. Even at distances far greater than the separation between the Sun and the planets, a passing star can perturb the delicate orbits of distant Oort cloud objects. Some of these perturbations push objects inward, sending them toward the inner solar system as long-period comets. Others push objects outward, weakening their binding to the sun until they drift away entirely. Over time, these encounters erode the outer cloud. So where exactly does the sun lose control? There is no single distance where an invisible line is crossed and an object suddenly becomes free. Instead, there is a gradual transition from strong binding to weak binding to statistical instability. Astronomers often describe this transition using the concept of a gravitational sphere of influence, sometimes called the Hill sphere. In a simplified two-body system, the Hill sphere defines the region around a body where its gravity dominates over that of a larger central mass. In the context of the Sun and the Milky Way, the Hill sphere represents the region where the Sun's gravity dominates over the average galactic gravitational field. Estimates of the Sun's Hill sphere radius vary, but they generally fall in the range of 1 to 2 light years. That is remarkably close to the estimated outer edge of the Oort Cloud. This is not a coincidence. The Oort Cloud appears to occupy much of the Sun's gravitational sphere of influence within the galaxy. Inside this region, objects are more likely to remain bound to the Sun over long periods. Outside it, they are more likely to be stripped away by galactic tides or captured by other stars. Even within the Hill sphere, stability is not guaranteed. Objects near the boundary may remain bound for millions of years and then be lost during a single stellar encounter. Others may drift in and out of marginal binding states repeatedly. This uncertainty makes the concept of losing its grip inherently probabilistic. At smaller distances, the Sun's grip is firm. At greater distances, it is tenuous. Somewhere in between lies a zone where belonging is temporary. This has important consequences for how we define the solar system. If we define the solar system as the region where the Sun's gravity is the dominant force, then the solar system extends far beyond the planets, far beyond the Kuiper belt, and deep into the Oort Cloud. If we define it as the region where objects are guaranteed to remain bound over the age of the solar system, then the boundary lies closer in, perhaps within the inner Oort Cloud. If we define it operationally, based on observed populations of objects, then the boundary becomes fuzzy again, stretching outward until the density of bound objects drops below detectability. Each definition yields a different answer, and none of them are wrong. Another way to approach this question is through energy. An object bound to the Sun has negative orbital energy relative to the Sun. An unbound object has positive energy. Objects near the outer Oort Cloud often have energies very close to zero. Small changes in velocity caused by galactic tides or stellar encounters can flip the sign. In that sense, the outer Oort Cloud is populated by objects living on the edge of escape. This edge is not static. It shifts as the Sun moves through different regions of the galaxy. When the Sun passes through denser stellar environments, encounters are more frequent and disruptive. When it passes through quieter regions, the cloud is more stable. Over the course of its orbit around the galaxy, the Sun has likely experienced many such environments. Early in its history, when it was part of a dense stellar cluster, close encounters may have stripped away large portions of the outer cloud. Later, as the Sun settled into a more isolated orbit, the remaining cloud stabilized. This history suggests that the present-day Oort cloud is not the original one. It is what remains after billions of years of erosion. That erosion continues today. Every stellar encounter slightly reshapes the cloud. Every galactic tide subtly alters orbits. The Sun is constantly losing some of its distant grip, even as it maintains control over its inner regions. This loss is slow. On human timescales, it is invisible. On cosmic timescales, it is inevitable. Another subtle aspect of losing grip involves capture. Just as the Sun can lose objects from its outer cloud, it can also gain them. Interstellar objects occasionally pass near the Sun. Most pass through without interaction, but under the right conditions, some could be captured into weakly bound orbits. If this happens, the outer Oort cloud could include objects that did not originate with the solar system at all. These objects would become part of the Sun's domain temporarily, perhaps for millions of years, before being lost again. This exchange blurs the distinction between solar system material and interstellar material. Ownership becomes a matter of timing rather than origin. An object may belong to the Sun now, belong to another star later, and wander freely in between. This perspective reframes the question of where the Sun loses its grip. Rather than asking for a static boundary, it may be more accurate to ask about residence time. How long does an object remain bound? How stable is that binding? How likely is it to persist over billions of years? Within the planetary region, residence times are effectively infinite on cosmic scales. Within the Kuiper belt, they are extremely long. Within the inner Oort cloud, they are long but not absolute. Within the outer Oort cloud, they are long but fragile. Beyond that, they become temporary. This gradient of stability is more informative than any single distance. It tells us that the solar system is not a closed system with rigid walls. It is an open system interacting continuously with its galactic environment. The sun's grip weakens gradually, not abruptly. It fades rather than breaks. That fading grip explains why the Oort cloud looks the way it does. It explains why long-period comets arrive sporadically. It explains why the cloud is sparse, extended, and vulnerable. It also explains why the Oort cloud may be one of the most dynamic parts of the solar system, despite its apparent stillness. Motion in this region is slow, but change is constant. As the sun continues its journey around the galaxy, it will keep losing and gaining distant companions. The outer cloud will continue to erode and reform. The boundary will continue to shift. From the perspective of the inner solar system, none of this matters very much. The planets will continue to orbit calmly. The sun will continue to shine. Life on Earth will remain unaware. But from a broader perspective, the outer Oort cloud represents the place where the solar system transitions from a tightly bound family to a loosely connected participant in the galaxy. It is where the sun's influence blends into the background of the Milky Way. An understanding that transition prepares us for the next question, which naturally follows. If the sun's grip weakens because of the galaxy and passing stars, then how exactly do those external influences shape the cloud? What role do neighbouring stars play, and how often do they disturb this distant region? Nothing in the galaxy stands still for very long, even if it appears that way from our limited perspective. The sun is moving, other stars are moving. Entire stellar systems drift along their own paths around the centre of the Milky Way. Over millions and billions of years, those paths occasionally bring stars closer to one another than we might expect. Not close in the sense of planetary distances, but close enough for gravity to notice. When two stars pass within a few light years of each other, their planets usually remain undisturbed. The distances between stars are vast compared to the sizes of planetary systems. But the outer Oort cloud occupies a region that stretches far enough outward to overlap with these interstellar approaches. That is where passing stars become important. To understand the role of stellar encounters, it helps to picture the sun travelling through a sparse but dynamic stellar environment. In our neighbourhood of the galaxy, the average distance between stars is roughly 4 to 5 light years. The sun's nearest neighbour, Alpha Centauri, lies about 4.37 light years away. That sounds comfortably distant, and on human timescales it is. However, stars are not fixed relative to one another. Over millions of years, their positions shift dramatically. Astronomers can measure the motion of nearby stars with remarkable precision. By tracing these motions forward and backward in time, they can estimate when close encounters occurred or will occur. These calculations reveal that close stellar passes are not hypothetical. They are routine on galactic timescales. A star may pass within 1 light year of the Sun every few 100,000 to a few million years. Closer passes are rarer but still possible. Over the 4.5 billion year history of the solar system, there have likely been many such encounters. Each encounter, even at distances of a light year or more, exerts a gravitational tug on the outer Oort cloud. The effect of this tug depends on several factors: the mass of the passing star, its relative velocity, and its closest approach distance. A massive star passing slowly at a relatively close distance will have a stronger effect than a small, fast-moving star that remains farther away. But even modest encounters can accumulate over time. Imagine an object at 50,000 astronomical units from the Sun. Its orbit is extremely elongated. Its gravitational binding energy is small. A passing star at a distance of 1 light year may slightly alter its velocity, perhaps changing it by a fraction of a metre per second. That sounds negligible, but at such weak binding it can be enough to reshape the orbit significantly. In some cases, the object's closest approach to the Sun may be lowered, sending it inward as a long-period comet. In other cases, the object may gain enough energy to become unbound entirely, drifting into interstellar space. This is how the outer Oort cloud slowly erodes, not in a catastrophic event, not in a dramatic collision, but through countless small gravitational nudges accumulated over billions of years. One of the most well-known examples of a past or future stellar encounter involves a star called Gliese 710. Astronomical calculations suggest that in about 1.3 million years, Gliese 710 will pass relatively close to the Sun, perhaps within 0.2 to 0.3 light-years. That is far beyond the orbit of Neptune. It is even beyond the Kuiper belt. But it lies well within the estimated outer boundary of the Oort cloud. When this encounter occurs, it is expected to disturb a significant number of Oort cloud objects. Over the following millions of years, the rate of long-period comets entering the inner solar system may increase. This will not threaten the planets directly in any immediate way. The probability of a comet striking Earth remains low. But statistically, the flux of comets will rise. Gliese 710 is only one example. There have been many such encounters in the past, and there will be many more in the future. Some may have been closer than the upcoming pass of Gliese 710. Others may have involved more massive stars producing stronger perturbations. In the early solar system, stellar encounters were likely even more common. The Sun is thought to have formed within a dense stellar cluster, where stars were packed much more closely together than they are now. In that environment, close passes would have been frequent. These early encounters may have played a major role in shaping the Oort cloud's initial structure. They could have helped to lift scattered Planier simals out of the flat plane of the early solar system and redistribute them into a spherical configuration. They may have stripped away some loosely bound objects before the Oort cloud fully formed. In this sense, passing stars were not just destructive agents. They were architects. They helped transform a flattened disk of scattered debris into a three-dimensional halo. Once the Sun left its birth cluster and entered a quieter galactic neighbourhood, the rate of close encounters decreased. The outer Oort cloud stabilised somewhat, though it remained vulnerable. The cumulative effect of these stellar encounters over billions of years is profound. Without them, the outer Oort cloud might look very different. It might be more disk-like, retaining more of its original alignment with the planetary plane. The nearly isotropic distribution of long-period comets suggests that stellar perturbations have been significant. Another important aspect of stellar encounters is asymmetry. When a star passes near the Sun, its gravitational influence is not evenly distributed across the Oort cloud. Objects on the side facing the passing star experience a stronger pull than those on the opposite side. This differential effect can stretch and distort the cloud temporarily. Over time, repeated encounters from different directions randomize these distortions, reinforcing the spherical shape. The orientation and velocity of the passing star also matter. A slow-moving star exerts a longer-lasting gravitational influence than a fast-moving one. Even if the closest approach distance is the same, a slower encounter can produce larger orbital changes. Mass plays a role as well. A red dwarf passing at 1 light-year may produce modest perturbations. A more massive star passing at the same distance could produce stronger effects. Fortunately, massive stars are less common in the galaxy, reducing the likelihood of extreme disruptions. Beyond individual stars, there are also larger-scale disturbances. The Sun's orbit around the Milky Way takes it through different galactic environments. It passes through spiral arms, regions with higher stellar densities and molecular clouds. These regions increase the likelihood of close encounters. Some researchers have proposed that periodic increases in comet activity in the inner solar system could be linked to the Sun's motion through such dense regions. While this idea remains debated, it highlights the connection between galactic motion and comet flux. Molecular clouds, in particular, can exert gravitational influence. These vast accumulations of gas and dust are far more massive than individual stars. If the Sun were to pass near or through a molecular cloud, the gravitational perturbations on the outer Oort cloud could be significant. Such events are rare, but over billions of years not impossible. All of these disturbances share a common feature. They operate slowly and subtly. There is no visible shaking of the solar system. The planets do not wobble dramatically. The inner solar system remains largely unaffected. Only the outermost region, the loosely bound halo of icy bodies, responds, and even then the response unfolds over millions of years. From the perspective of Earth, the result is an occasional long-period comet, arriving unexpectedly from a random direction, glowing briefly in the sky before departing again for tens of thousands or millions of years. Each such comet is evidence of a distant disturbance. It is a messenger not only from the Oort Cloud, but from the Sun's galactic environment. Another intriguing possibility involves close stellar passages that may have already occurred but left subtle traces. Some unusual objects in the outer solar system, such as Sedna, and similar bodies with highly elongated and detached orbits, may bear the imprint of an early stellar encounter. Their orbits are difficult to explain through interactions with the known planets alone. If a star passed relatively close during the Sun's early history, it could have reshaped the outer regions and left behind a population of objects with distinctive orbital characteristics. Studying these objects provides indirect evidence of ancient stellar encounters. In this way, the Oort Cloud serves as a historical record. Its structure encodes information about the Sun's past interactions with neighbouring stars. Each perturbation leaves a subtle mark on the distribution of orbits. Over billions of years, these marks overlap and blend, but patterns remain. The fact that the Oort Cloud still exists at all suggests that most stellar encounters have not been catastrophic. They have been gentle enough to reshape rather than destroy. But that balance is delicate. If a star were to pass extremely close, within a fraction of a light year, the outer Oort Cloud could be severely disrupted. A significant fraction of its objects could be stripped away in a relatively short time. Such close encounters are rare in the Sun's current environment, but not impossible over cosmic timescales. This brings us back to the idea of the solar system as an open system. The outer Oort Cloud is not sealed off. It is exposed to the galaxy. Passing stars and galactic tides continually influence it. The Sun does not hold its distant companions in isolation. It holds them in a dynamic, interactive gravitational landscape. Understanding this landscape helps explain why the Oort Cloud is so vast yet so fragile. It exists at the threshold where stellar systems meet. If passing stars and galactic forces shape the Oort Cloud so profoundly, could other stars have similar structures? Do most stars possess their own distant clouds of icy debris? And if so, how common are these extended gravitational halos throughout the galaxy? Occasionally, without warning, something ancient enters the inner solar system and briefly steals the sky. It arrives from a direction with no obvious connection to the planetary plane, brightens as it approaches the Sun, grows a tail that can stretch for millions of kilometres, and then fades again, often never to return. These visitors are comets, and for our purposes they are far more than beautiful curiosities. They are evidence. Everything we think we know about the Oort Cloud rests, in one way or another, on the behaviour of comets. Without them, the idea of a vast, distant reservoir of icy bodies would be little more than speculation. With them, it becomes difficult to argue that such a reservoir does not exist. To understand why, it helps to look closely at what comets are and what makes long-period comets so unusual. A comet is essentially a frozen remnant from the early solar system. Its nucleus is a compact mixture of water ice, carbon dioxide ice, carbon monoxide ice, ammonia, methane, and rocky dust. These materials condensed in the cold outer regions when the planets were forming, billions of years ago. For most of their existence, comets remain inert, locked in darkness at temperatures only a few degrees above absolute zero. Nothing about them is active or dramatic until they approach the Sun. As a comet moves inward, solar radiation begins to heat its surface. Ices that have remained solid for billions of years start to sublimate directly into gas. This gas carries dust with it, forming a glowing envelope called a coma around the nucleus. Solar radiation pressure and the solar wind then push this material outward, creating the familiar tails. The spectacle we see is temporary. Once the comet moves away from the Sun, activity fades, the gas disperses, the dust spreads out. What remains is the same small, dark nucleus continuing along its orbit. Short-period comets, those that return every few years or decades, mostly originate in the Kuiper belt. Their orbits are relatively well understood. They tend to lie near the plane of the planets. They return again and again until they exhaust their volatile material or are ejected. Long-period comets are different. Their orbital periods range from tens of thousands to millions of years. Many are observed making what appears to be their first and only visit to the inner solar system. Their orbits are highly elongated, and their inclinations are randomly distributed. One may plunge inward from far above the plane of the planets, another may arrive from far below. There is no preferred direction. This randomness is the key. If all comets originated in a flat disk like the Kuiper belt, we would expect their orbits to cluster near that plane. That is exactly what we see with short-period comets. The long-period ones refuse to follow that pattern. Instead, they behave as though they are being drawn from a spherical source surrounding the Sun. That source, by necessity, must lie far away. The energies of long-period comets tell the same story. When astronomers calculate their original orbits, accounting for planetary perturbations, many of these comets appear to have started their journey at distances of tens of thousands of astronomical units. Some are so weakly bound that even small uncertainties in their velocity determine whether they are technically bound to the Sun or already on an escape trajectory. This is not what you would expect if their source were nearby. The Oort Cloud was proposed specifically to explain these observations. It provides a natural explanation for both the isotropic distribution of long-period comet orbits and their extreme energies. In this context, comets are not random debris. They are messengers from the deep freeze, carrying information from regions we cannot observe directly. Each long-period comet that enters the inner solar system is like a probe launched unintentionally, delivering a brief data packet before vanishing again into the dark. The rate at which these messengers arrive is also informative. On average, a few new long-period comets are discovered each year. Some are faint and go unnoticed. Others become spectacular, visible even to the naked eye. When astronomers correct for observational bias, they can estimate how many such comets likely enter the inner solar system annually. From that rate, they can infer how large the distant reservoir must be to sustain it over billions of years. The conclusion is unavoidable. The source must be enormous. If the Oort Cloud contained only a few million objects, it would have been depleted long ago. The steady trickle of long-period comets we observe today implies a population in the hundreds of billions or trillions. This inference is one of the strongest arguments for the Oort Cloud's existence. There's also a chemical dimension to this story. When comets are observed up close, either through telescopes or spacecraft missions, their composition reveals information about the conditions in which they formed. Many contain volatile compounds that would not survive repeated heating near the Sun. Their presence suggests that these objects have spent most of their existence far from solar warmth. Some long-period comets appear chemically pristine, showing fewer signs of processing than short-period comets that have made many close passes. This supports the idea that they have been stored in deep cold for billions of years. The Oort Cloud provides exactly such a storage environment. Another clue comes from the distribution of comet energies. Astronomers notice a clustering of long-period comet energies near zero. This suggests that many are arriving from a region where they were only barely bound to the Sun. That is consistent with an origin near the outer edge of the Sun's gravitational sphere of influence. If comets were coming primarily from closer regions, their energies would be more strongly negative. The observed distribution points outward, not inward. There is also a population known as dynamically new comets. These are comets whose orbits suggest they have never passed close to the Sun before. They are pristine arrivals, entering the inner solar system for the first time. Their existence implies a vast reservoir that has remained largely untouched. Once a comet enters the inner solar system, its fate is uncertain. Some are ejected entirely after one pass, flung out by interactions with the giant planets. Others are captured into shorter period orbits. Many gradually disintegrate. This means that the Oort Cloud is not only a source but also a sink. Objects are constantly being removed from it, and yet the cloud persists. This persistence is another argument for its immense size. Now consider the timing. Long-period comets do not arrive in neat intervals. Their appearances are irregular. There may be years with several notable comets, followed by long quiet periods. This randomness reflects the chaotic nature of the perturbations that send them inward. Passing stars, galactic tides, and the combined gravitational effects of the planets all play roles. A small change in an object's orbit far out in the cloud can take millions of years to translate into an inward plunge. This means the comets we see today may have been disturbed long before humans existed. In some cases, the perturbation that set a comet on its current path may have occurred tens of millions of years ago. Perhaps during a close stellar encounter the Sun has long since left behind. So when a comet suddenly appears in our sky, It is not a spontaneous event. It is the delayed consequence of ancient gravitational interactions. This time lag adds another layer to their role as messengers. They're carrying information not only from distant space, but from deep time. Another intriguing aspect involves comet showers. Models suggest that particularly close stellar encounters can trigger bursts of comet activity, sending many objects inward over extended periods. These events, called comet showers, may last millions of years. Some researchers have explored whether such showers could be linked to mass extinction events on Earth, though this remains controversial. The evidence is not conclusive, and many extinctions are better explained by other mechanisms. Still, the possibility underscores the influence of distant gravitational disturbances on the inner solar system. The Oort Cloud is not isolated. Its behaviour can have consequences far closer to home. Comets also provide constraints on the cloud's shape. The nearly uniform distribution of long-period comet inclinations suggests that the outer Oort Cloud is close to spherical. Any significant flattening would leave a detectable signature in the arrival directions. This spherical symmetry is difficult to produce without the combined effects of stellar encounters and galactic tides acting over long periods. It reinforces the idea that the cloud has been shaped by its environment, not just by the Sun alone. Short-period comets, by contrast, tell us about the Kuiper belt. Their different behaviour helps distinguish the two populations. Together, these comet populations form a kind of diagnostic tool. By studying their orbits, energies, and compositions, astronomers can piece together the structure of regions that cannot be observed directly. It is worth emphasising how indirect this process is. No one has ever pointed a telescope at the Oort Cloud and seen it. No spacecraft has ever entered it. Everything we believe about it comes from these fleeting visitors and from the laws of gravity applied consistently. This makes comets uniquely valuable. They are not just debris, they are data. Another important detail is that not all long-period comets necessarily originate from the outermost regions. Some may come from the inner Oort Cloud, where objects are more tightly bound. These comets tend to have slightly different energy distributions. This distinction supports the idea of a layered cloud. The inner cloud supplies the outer cloud supplies the comets. Over time, this flow maintains the population we observe. This layered structure also helps explain why the comet flux has remained relatively steady over billions of years, despite ongoing losses. Now think about visibility. Most long-period comets are faint. Only a small fraction become bright enough to attract public attention. Many pass through the inner solar system unnoticed, detected only by automated surveys or not at all. This means that the visible comets represent only the tip of the iceberg. For every bright comet that makes headlines, there may be dozens or hundreds that go unseen. Each one still represents a perturbation in the distant cloud. In that sense, the Oort Cloud is far more active than it appears. Its influence is continuous, even if our awareness of it is sporadic. Comets also remind us of scale in a more visceral way. A long-period comet's journey inward may take millions of years. Its visible phase may last months. Then it disappears again for eons. This ratio of visibility to invisibility mirrors the Oort Cloud itself. Vast, persistent, mostly unseen, revealing itself only briefly and indirectly. When you put all of this together, comets cease to be curiosities. They become the strongest evidence we have that the solar system extends far beyond the planets, beyond the Kuiper belt, and deep into a distant, cold halo. They are the reason the Oort Cloud is taken seriously, rather than dismissed as speculation. They are the reason astronomers can talk about distances of tens of thousands of astronomical units with confidence rather than hesitation. And they are the reason the Oort Cloud feels less abstract and more real, even though it remains invisible. If comets are messages from the deep freeze, what exactly are they telling us about where they come from? And more broadly, is the Oort Cloud truly something that belongs only to the Sun, or is it part of a larger pattern, repeated around other stars throughout the galaxy? Ownership sounds simple when we talk about planets. Earth orbits the Sun. Jupiter orbits the Sun. Their gravitational relationship is obvious, stable, and long-term. But once we move outward into the distant halo of icy bodies, the idea of ownership becomes less straightforward. The Oort Cloud challenges the assumption that the solar system is a neatly contained structure, belonging exclusively to one star. To explore whether the Oort Cloud is truly ours, we first need to clarify what belonging means in a gravitational sense. In astronomy, an object belongs to a star if it is gravitationally bound to that star. In simple terms, its total orbital energy relative to the star is negative. That means it does not have enough speed to escape permanently. It may wander far away, but gravity will eventually pull it back. By that definition, most objects in the Oort cloud are part of the solar system. They orbit the Sun, even if those orbits take millions of years to complete. However, the strength of that binding varies enormously. A planet like Earth is deeply bound. To remove Earth from the Sun's gravitational influence would require a massive energy input. The same is true for Jupiter or Saturn. Even Neptune, far from the Sun compared to the inner planets, is securely anchored. An object at 50,000 astronomical units is different. It is bound, but weakly. A small change in velocity, perhaps delivered by a passing star or galactic tide, could be enough to unbind it completely. This weak binding means that Oort cloud membership can be temporary on cosmic timescales. An object might remain bound for hundreds of millions of years, and then be lost during a stellar encounter. Another object might drift into the Sun's gravitational sphere of influence and become bound after previously wandering freely through interstellar space. So if ownership is defined strictly by current gravitational binding, then yes, the Oort cloud is ours, but only provisionally. Another angle on this question involves origin. Did every object in the Oort cloud form within the solar system? The prevailing theory suggests that most did. During the early stages of planetary formation, countless icy planetesimals were scattered outward by interactions with the giant planets. Many were ejected entirely. Others were placed on elongated orbits that eventually evolved into the Oort cloud. These objects would indeed be native solar system material, remnants of the same primordial disk that formed the planets. But that is not the whole story. The Sun was not born in isolation. It likely formed within a cluster of stars, perhaps containing hundreds or thousands of stellar siblings. In such an environment, close encounters would have been common. During those early interactions, material could have been exchanged. Computer simulations show that it is possible for stars in a cluster to capture planetesimals from one another, especially if relative velocities are low. This means that some fraction of the Oort cloud may consist of objects that formed around other stars. If that is true, then part of what we call the Oort cloud may not have originated here at all. More recently, we have direct evidence that interstellar objects exist. The discovery of Oumuamua in 2017 and Comet Borisov in 2019 confirmed that small bodies can travel between star systems. These objects pass through the inner solar system on hyperbolic trajectories, clearly unbound to the Sun. Most interstellar visitors likely pass through unnoticed, especially if they never come close to the Sun. Under the right conditions, however, capture is theoretically possible. If an interstellar object passes near the Sun at a low relative speed and experiences a gravitational interaction with one of the giant planets, it could lose enough energy to become bound. If captured into a distant elongated orbit, it might join the Oort cloud. Such captures are expected to be rare, but over billions of years, rare events accumulate. This possibility complicates the idea of ownership further. If some Oort cloud objects originated elsewhere, and if some originally solar system objects have been lost to other stars, then the Oort cloud becomes less a private domain and more a shared reservoir within the galaxy. The boundary between solar system material and interstellar material becomes porous. Another consideration involves overlapping gravitational spheres of influence. As discussed earlier, the Sun's gravitational sphere extends perhaps 1 to 2 light-years. The nearest star systems have their own spheres of influence. In some regions of space, especially within stellar clusters, these spheres can overlap significantly. During close stellar encounters, objects in the outer Oort cloud may temporarily experience comparable gravitational forces from both stars. Some may be transferred from one star's cloud to another. This exchange mechanism suggests that Oort-like clouds around different stars are not entirely isolated. They may interact, especially in the early stages of stellar evolution, when stars are closer together. This leads to a broader question. Is the Oort cloud unique to the Sun? The processes that formed it, planet formation, gravitational scattering by giant planets, stellar encounters, are not unique. Observations of exoplanetary systems reveal that giant planets are common, stellar clusters are common, galactic tides affect all stars orbiting within the Milky Way. Given these similarities, it would be surprising if the Sun were the only star with a distant halo of icy bodies. While we cannot observe Oort clouds around other stars directly, theoretical models suggest that they should be widespread. Many stars with planetary systems likely possess their own distant reservoirs of icy debris. If that is true, then the Oort cloud is not a rare anomaly. It is a typical byproduct of planetary system formation. That realization changes the emotional framing of the question. Instead of asking whether the Oort cloud truly belongs to us, we might ask whether any Oort cloud truly belongs to any star. These structures may be common features of stellar systems, shaped by local dynamics, but influenced by the shared galactic environment. Ownership in this context becomes relative rather than absolute. There's also a temporal dimension to consider. Right now, most Oort cloud objects are bound to the Sun. In the distant future, that may not be true. As the Sun continues its orbit around the Milky Way, it will encounter new stellar neighbours. Over billions more years, it will likely lose additional outer cloud objects. Some may be captured by other stars. Others may drift freely in interstellar space. Eventually, when the Sun exhausts its nuclear fuel and evolves into a red giant and then a white dwarf, the gravitational environment of the solar system will change. Mass loss during the red giant phase will weaken the Sun's gravitational hold, causing planetary orbits to expand and potentially unbinding some distant objects. The outer Oort cloud, already tenuous, could be significantly depleted during this phase. In that far future, the idea that the Oort cloud belongs to the Sun may no longer apply in any meaningful sense. This long-term perspective reinforces the idea that gravitational ownership is always conditional. On timescales of human civilization, the Oort cloud is part of the solar system. On timescales of galactic evolution, it is a transient structure. Another interesting aspect involves the philosophical meaning of hours. When we speak of the solar system, we often include everything gravitationally bound to the Sun. By that definition, the Oort cloud is ours as much as Neptune is. But the psychological distance is enormous. Neptune can be imaged clearly. Its orbit is well measured. Spacecraft have visited it indirectly through flybys of its moon Triton. The Oort cloud remains invisible and unreachable with current technology. Even our fastest spacecraft have barely begun to leave the heliosphere, the bubble carved by the solar wind, which itself lies far inside the Oort cloud's inner boundary. Voyager 1, after decades of travel, has reached a distance of roughly 160 astronomical units. That is still less than 10% of the distance to the inner Oort cloud, so while the Oort cloud is technically part of the solar system, it remains practically inaccessible. This practical inaccessibility makes it feel less like ours, even though gravitationally it is. There is also the question of influence. The planets influence one another significantly. Jupiter shapes asteroid orbits. Saturn affects comet trajectories. Neptune sculpts the Kuiper belt. The Oort cloud, by contrast, exerts almost no influence on the inner solar system except through rare comet arrivals. It is part of the system, but it is not central to its daily dynamics. This marginal role reinforces the sense that it is peripheral, an outer archive rather than an active participant. Yet in terms of sheer size, it dominates. If we define the solar system by its gravitational reach, then the Oort cloud represents the majority of its physical extent. The planets occupy a tiny inner fraction, so in terms of space, the Oort cloud is more representative of the solar system's size than the planetary region. This contrast between physical extent and practical significance adds another layer to the ownership question. In one sense, the Oort cloud is the solar system's outermost domain. In another, it is a loosely connected appendage, constantly influenced by the galaxy. Perhaps the most accurate answer is that the Oort cloud is both ours and not entirely ours. It is ours in that it formed largely from solar system material, is currently bound to the Sun, and defines much of the Sun's gravitational territory. It is not entirely ours in that its outermost members are weakly bound, subject to galactic forces, and potentially exchanged with other stars over time. It sits at the interface between the Sun and the galaxy. That interface is not a wall, it is a gradient. Step outside the Sun's most distant companions, and the environment changes in a way that is subtle rather than dramatic. There is no gate, no sudden emptiness, no sign announcing that one domain has ended and another has begun. Instead, the solar system gradually blends into something larger, quieter, and far less personal. This is the interstellar neighbourhood. the region of space where the Sun is no longer the primary reference point, and where the galaxy itself becomes the dominant presence. To understand what lies beyond the Oort Cloud, it helps to release the idea that interstellar space is a void. It is not empty in any meaningful sense. It is thin, yes, but it is structured. It contains gas, dust, magnetic fields, cosmic rays, and the faint gravitational influence of countless stars moving along their own trajectories. The transition from the Oort Cloud into this broader environment is not marked by distance alone. It is defined by influence. Inside the Oort Cloud, even at its most distant edges, the Sun still matters. Its gravity may be weak, but it remains the single most important force acting on bound objects. Beyond that region, the balance shifts. The Sun becomes just one gravitational contributor among many. At that point, an object's motion is shaped more by the collective mass of the Milky Way than by the star it once orbited. The interstellar neighbourhood begins, loosely speaking, where the probability of long-term solar binding drops sharply. Objects passing through this region are no longer reliably captured by the Sun, nor are they guaranteed to remain associated with it if they are temporarily bound. Their trajectories are shaped by galactic tides, nearby stars, and the overall gravitational landscape of the galaxy. This region is not static. It is dynamic on vast timescales. The Sun itself is moving through it. Right now, the Sun is travelling through a region known as the local interstellar cloud, sometimes called the local fluff. This is a slightly denser patch of interstellar gas embedded within a much larger, lower density cavity called the local bubble. The local bubble is thought to have been carved out by ancient supernova explosions, leaving behind a region of hot, diffuse gas. Within this environment, the density of matter is extremely low by terrestrial standards, but not negligible. There are a few atoms per cubic centimetre, mostly hydrogen and helium, along with trace amounts of heavier elements. There is also dust, microscopic grains drifting slowly through space. The Sun ploughs through this material as it orbits the galaxy, and its motion shapes the heliosphere, the bubble carved out by the solar wind. The heliosphere marks a magnetic boundary, not a gravitational one, and it lies far inside the Oort Cloud. Beyond the heliopause, where the solar wind gives way to interstellar plasma, the Sun's magnetic influence fades, but gravity continues much farther. Still, once you move beyond the outer Oort Cloud, gravity alone is no longer enough to define a system. Objects in the interstellar neighbourhood are influenced by the combined mass of billions of stars, as well as dark matter, which makes up a significant fraction of the galaxy's mass. This background gravitational field sets the baseline motion for everything in the Milky Way. In this environment, stars are not isolated islands. They are participants in a shared dynamical system. Each star carries with it a small region where its gravity dominates, but those regions overlap and interact. The farther you move from any given star, the more its influence blends into the galactic background. This blending is why the concept of between stars is misleading. There is no sharp boundary where one star's domain ends and another's begins. There are only regions where one influence outweighs another. The interstellar neighbourhood is where those weights become comparable. Another important feature of this region is relative motion. Stars do not sit still with respect to one another. They move at different speeds and in different directions around the galactic centre. Some move faster, some slower. Some oscillate above and below the galactic plane. Over time, these motions cause stars to drift past one another. From the Sun's perspective, nearby stars appear to approach and recede over millions of years. Today's neighbours were not yesterday's neighbours, and they will not be tomorrow's. This constant reshuffling means that the interstellar neighbourhood is ever-changing. The Sun's nearest stellar neighbour at any given moment is not fixed. Over the Sun's lifetime, many stars have passed closer than Alpha Centauri is today. Some will do so in the future. Each close pass slightly reshapes the gravitational environment of the outer solar system. This is why the Oort Cloud and the interstellar neighbourhood cannot be treated as separate realms. They are coupled. The outermost Oort Cloud exists within the interstellar neighbourhood. It is shaped by it. It responds to it. Beyond the Oort Cloud, objects do not orbit the Sun in any meaningful sense. Instead, they follow paths determined primarily by the galaxy. Some of these objects are free-floating, never bound to any star. Others may have been ejected from planetary systems long ago. Some may have formed in isolation within collapsing gas clouds. We know such objects exist because we have detected them indirectly. Gravitational microlensing surveys suggest that there may be enormous numbers of free-floating planets in the Milky Way, perhaps even more than there are stars. These objects wander through interstellar space without a parent star, shaped only by the galaxy's gravitational field. In addition to rogue planets, there are countless smaller bodies: asteroids, comet-like objects, dust grains, and gas clouds. Occasionally, some of these wanderers pass through the solar system. The discovery of Oumuamua in 2017 was the first confirmed detection of an interstellar object passing through our neighbourhood. Its trajectory was hyperbolic, meaning it was not bound to the Sun. It came from outside the solar system and left again, never to return. 2 years later, comet Borisov was detected on a similar path. Unlike Oumuamua, it displayed classic cometary activity, confirming that icy bodies can travel between stars. These discoveries were not surprises in a theoretical sense. They were expected. What surprised astronomers was how detectable they were, suggesting that interstellar objects may be more common than previously thought. If that is the case, then the interstellar neighbourhood is not empty of solid bodies. It is populated quietly by debris from countless star systems. This population overlaps spatially with the outermost regions of the Oort Cloud. From a gravitational perspective, the distinction between a loosely bound Oort Cloud object and a passing interstellar object can be thin. The difference may come down to a small change in velocity. An object moving slightly slower relative to the Sun may become temporarily bound. One moving slightly faster will pass through and leave. This sensitivity reinforces the idea that the outer boundary of the solar system is not a line but a zone of exchange. Another defining feature of the interstellar neighbourhood is timescale. Motion here is slow. Not slow in an absolute sense, but slow relative to human perception. A star passing within a light year of the Sun may take tens of thousands of years to approach and tens of thousands more to recede. The gravitational influence builds gradually and fades gradually. For objects in the outer Oort Cloud, this slow change is significant. Their weak binding allows these gradual forces to accumulate, altering orbits without dramatic events. In the deeper interstellar neighbourhood, objects are not bound long enough for such slow accumulation to matter in the same way. Their paths are governed by broader galactic dynamics. The galaxy itself rotates. Stars orbit the galactic centre on timescales of hundreds of millions of years. Superimposed on that motion are smaller oscillations, epicycles and vertical movements through the galactic plane. The Sun participates in all of these motions. As it moves, the environment around it changes. Gas density varies, stellar density varies, gravitational perturbations vary. This means the interstellar neighbourhood is not uniform. There are quieter regions and busier ones, regions with few nearby stars and regions with many, regions dominated by diffuse gas and regions influenced by molecular clouds. Over the Sun's lifetime, it has passed through several such environments and will pass through many more. Each passage subtly affects the outskirts of the solar system. This dynamic context helps explain why the Oort Cloud looks the way it does today. It is not merely a product of early solar system formation. It is the result of billions of years of interaction with the interstellar neighbourhood. In that sense, the Oort Cloud is as much a galactic structure as a solar one. Beyond it, the interstellar neighbourhood continues without regard for any single star. Distances between stars average several light years, but those distances are not empty corridors. They are filled with the collective influence of the galaxy. Light travels through this region carrying information from distant stars. Cosmic rays propagate through it, shaped by magnetic fields. Dust grains drift slowly, sometimes accumulating, sometimes dispersing. Occasionally, shock waves from supernovae sweep through, compressing gas and triggering new star formation elsewhere. The solar system is embedded in this environment, not isolated from it. The interstellar neighbourhood also provides context for how we think about scale and belonging. From Earth, the Sun feels like the centre of everything. From the perspective of the galaxy, it is one star among hundreds of billions, moving along a prescribed orbit shaped by the galaxy's mass distribution. The Oort Cloud marks the region where that broader perspective begins to matter more than the local one. Beyond it, the Sun's identity fades into the background of the Milky Way. This does not mean the solar system becomes insignificant. It means it becomes one participant in a much larger system. Understanding this helps avoid a common misconception. When people imagine leaving the solar system, they often picture a dramatic exit, a moment when everything familiar falls away and something fundamentally different begins. In reality, the transition is gentle. The interstellar neighbourhood begins quietly. The sun does not abruptly lose its influence. It gradually shares it. The Oort cloud does not suddenly stop. It thins, frays, and blends. This blending is a defining characteristic of gravitational systems on large scales. Another implication of this blending is that the galaxy may be filled with overlapping halos. If most stars have Oort-like clouds, then the interstellar neighbourhood may be threaded with countless overlapping regions of weak gravitational influence. These halos may intersect, exchange material, and reshape one another over time. In dense stellar environments such as star clusters or the galactic centre, these interactions would be even more frequent. In quieter regions like the Sun's current location, they occur more slowly, but they still occur. This picture transforms how we think about the structure of the galaxy. Rather than a collection of isolated stars with neat boundaries, the Milky Way becomes a web of overlapping gravitational domains, constantly interacting at their fringes. The Oort cloud is our local expression of that web. Beyond it lies not emptiness, but continuity. Stand back for a moment and picture the entire structure at once. Not just the planets, not just the Kuiper belt, not even just the distant halo of icy bodies we've been slowly mapping in our minds. Picture the Sun as a small gravitational centre embedded inside a sphere that stretches nearly halfway to the nearest star, a sphere so vast that the region we usually call the solar system occupies only a tiny inner fraction of it. That is the scale we have been unfolding. We began close to home, where distances can still be expressed in astronomical units without discomfort. We moved past Neptune, through the Kuiper belt, across the scattered disk, and outward into a region where numbers expanded rapidly. We watched the inner Oort cloud emerge as a hidden reservoir, more tightly bound and quietly maintaining balance. We followed the outer Oort cloud outward to its tenuous boundary, where the Sun's gravitational authority begins to fade into the broader influence of the Milky Way. Now, at this edge, the concept of an ending feels less appropriate than the concept of drifting. The outer Oort cloud does not form a wall, it forms a gradient. Objects become fewer, binding becomes weaker, external influences grow stronger. Eventually, the distinction between solar and interstellar becomes a matter of probability rather than certainty. This is the solar system's outermost posture, not rigid, not sharply defined, but gently dissolving into its surroundings. The phrase edge of forever sounds dramatic, but the reality is quieter than that. There is no dramatic drop-off into nothingness. There is only a shift in dominance, a slow handoff from one gravitational authority to another. Inside this enormous sphere, icy bodies orbit so slowly that a single revolution may take millions of years. Their temperatures remain near absolute zero. Sunlight reaches them faintly, and then fades into the general starlight of the galaxy. Most of these objects will never be seen. Most will never enter the inner solar system. They will simply continue their silent paths, shaped by forces too gradual to notice on short timescales. And yet, occasionally, one is nudged. A passing star shifts its orbit slightly. The galaxy's tidal field stretches it just enough. Its closest approach to the Sun drops. Over thousands or millions of years it falls inward. It becomes visible. It grows a tail. It arcs across our sky for a few months and then disappears again. That brief appearance is the only sign that the vast halo exists. Without those comets, the Oort cloud would remain entirely theoretical. With them, it becomes difficult to deny that the Sun's reach extends far beyond the region of planets. This leads to a perspective shift. If someone asks how big the solar system is, the honest answer depends on what you include. If you mean the region of major planets, it fits comfortably within a few dozen astronomical units. If you mean the Kuiper belt, it stretches to perhaps 50. If you include the scattered disk, you move into the hundreds. But if you define the solar system as everything gravitationally bound to the Sun, then the answer grows to tens of thousands of astronomical units, perhaps more than a light year in radius. That is a difference of 3 orders of magnitude. On that larger scale, the planets are not the defining feature of the solar system, they are its dense inner core. The Oort Cloud is what sets its true spatial extent. This realization can feel disorienting. We're accustomed to thinking of the solar system as something compact and tidy. A central star, a series of orbiting planets, perhaps a belt of asteroids and icy debris beyond. That picture is not wrong, but it is incomplete. The fuller picture is more diffuse. It includes a spherical halo that merges gradually into the galaxy. It includes objects that may not have formed here. It includes bodies that will not remain here forever. It includes exchange. Over billions of years, the Sun has likely lost some of its distant objects to interstellar space. It may have captured others. The Oort Cloud may contain material that once orbited another star. Other stars may host fragments that once belonged to the Sun. In that sense, drifting at the edge of forever is not just a poetic phrase. It is a physical description. The outermost objects are not firmly anchored. They drift in weak gravitational currents. They reside in a region where belonging is temporary and influence is shared. This drifting also has a temporal dimension. The Sun itself will not last forever in its current state. In roughly 5 billion years, it will exhaust the hydrogen in its core and expand into a red giant. During that process, it will lose mass. Its gravitational grip will weaken. Planetary orbits will expand. Some objects currently bound may become unbound. The outer Oort cloud, already fragile, will likely shed a significant fraction of its population. After the Sun becomes a white dwarf, its gravitational sphere of influence will be smaller. The Oort cloud, as we know it today, will not exist in the same form. This future reminds us that even large-scale structures are temporary. The Oort cloud has likely been evolving since the earliest days of the solar system. It was shaped by the Sun's birth cluster, by early stellar encounters, by planetary migration. It has been eroded by passing stars and galactic tides. It will continue to change. So when we ask how big the Oort cloud really is, the answer is not fixed. It depends on time as well as distance. Today, it may extend to 50,000 or 100,000 astronomical units. In the past, it may have been larger. In the future, it may be smaller. The edge drifts. This drifting does not make the Oort cloud less real. It makes it more dynamic. It is not a frozen boundary drawn once and for all. It is a living interface between a star and its galaxy. There is something quietly humbling about that. The region that defines the true size of our solar system is one we cannot see directly. It is one we cannot visit with current technology. It is inferred from subtle clues and long-term statistical patterns. It exists mostly in darkness and extreme cold, and yet it shapes how we understand our place in the galaxy. Because if the solar system extends nearly halfway to the nearest star, then we are not living in a small, isolated bubble. We are embedded in a gravitational structure that brushes against others. Stars are not separated by empty voids. Their outer halos overlap. Their influences interact. The galaxy is not just a collection of points of light. It is a web of extended domains. The Oort cloud is our local expression of that web. It marks the place where the Sun's influence fades, but does not abruptly end. It marks the region where galactic forces begin to matter as much as local ones. It marks the threshold between the familiar architecture of planets and the broader dynamics of the Milky Way. From Earth, none of this is visible. The night sky does not reveal the Oort cloud as a glowing sphere. It does not outline the Sun's gravitational boundary. What we see are stars scattered across the darkness. But hidden within that darkness is a region of space that belongs, loosely and temporarily, to the Sun. When you think about the scale again, it becomes clear why the question, how big is the Oort cloud, cannot be answered with a single number that satisfies intuition. It is as big as the Sun's gravitational patience allows. It is as big as the galaxy permits. It is as big as the delicate balance between binding and escape. And that balance is not static. The outermost objects are drifting, always. Some are drifting inward, becoming comets. Some are drifting outward, becoming interstellar wanderers. Some are simply circling slowly, unnoticed, for millions of years,